Okay,
Okay, so
I'm ready.
let me introduce the speaker. It's a great pleasure to introduce Sagar Shrivastava. Um, and he is going to talk, he's from TIFR, and he's going to talk about his PhD thesis. And his talk is on representations, determinants, and branching roots. Sagar.
Thank you, Gaurav, for the wonderful introduction. Um, I'm sorry for the initial technical glitch which was there. So, as Gaurav said, this is some work which I have done in my thesis along with Professor C.S. Rajan. So, let me get started with the things which I have mentioned over here. So, first, let's go to representations. Okay. So, when we say representation, we initially start with a group. And a representation, which I mean, in our language, we call it to be a G invariant space or a G module. It is nothing but just a group homomorphism from G to some GLB. And note that we never specify whether we are working with a finite dimensional vector space or G is finite, because this is a very general definition. Now, if I say V is a finite dimensional vector space, then this becomes a finite dimensional representation. If G is a finite group, then this becomes a representation of a finite group. So also the underlying field over here is important. And because you're working in the realm of vector spaces, and if let's assume for now, I mean, for everything that I'll be talking about beyond this, we'll be working with finite dimensional vector spaces. So we have got this trace. So for every element of GLB, I can define a trace. And what we're saying is that the trace of this morphism at a given element, that is what we call as the character at that given element. You see that with this definition, this trace becomes something which would be invariant in a conjugacy class. Okay. And as I said, I mean, the underlying field also is important. So if the field is some F, then so here for us, the F would be nothing but just complex numbers. Okay. But in general, we can have F representations. Okay. Let's work with some examples. So here, if we look at the So in this case, if you look here, I can have any sort of a phi working in, right? So phi could be a trivial morphism, that is taking every element to the identity, which gives us the trivial representation. So every group admits a trivial representation, and one of the non-trivial representations would be, sorry. So one of the non-trivial representations would be Sn acting on an n-dimensional vector space by permuting the basis. And then what we do is we just extend this linearly to the whole vector space. So this is a non-trivial action, and one will see some of this in the coming few slides. And an interesting one would be that if in this morphism over here, if this G itself was GLB, so I could have very well chosen this psi to be nothing but just the identity morphism, and then I can talk about the representation of it. So that also is a representation, and that is the one that I am most interested in. These are, so GLB over here is a Lie group. It's a reductive Lie group. We'll come to that later. Let's get some definitions precisely out. So first is what we call as reducible and irreducible. So a representation V is called reducible if I can write it as a direct sum of two representations, V1 and V2, such that both of them are non-zero and G invariant. Now, G invariant, as I had mentioned in the first slide, this is another word for for a representation of G. Okay. And if it is not reducible, that is, if it cannot be written as a sum of two, then it is called irreducibles. Now, to an extent, we can say that irreducible representations are like what atoms are for molecules. I mean, irreducible representations make up every representation. But we have to be very particular over here. There is something which is called as complete reducibility, which says that every constituent of a representation is coming from irreducibles. There are things which are not completely reducible, where this statement that all representation things would not hold. So let's come back to the action of Sn. So here we are limiting ourselves to the action of S3. And we'll see that this action of Sn or S3 on this three-dimensional vector space spanned by V1, V2, V3. And the action is via permutation of the basis. Now, one can work this out for any general Sn as well, but I'm showing here for S3 because it is a non-trivial, first non-trivial case over here. So look at this example, V1, which is given by the span of V1 plus V2 plus V3. Okay. Now, this is going to be J invariant because any permutation would take V1 plus V2 plus V3 to the same element. And one can check that this V2, which is given by V2 minus V1 and V3 minus V1. So this is also going to be invariant under permutations from S3. This is to say that, also the direct sum of V1 and V2, this would be the whole of V. So now we have written V as a direct sum of two S3 invariant vector spaces, which goes on to say that this is not reducible. So the question is that when that are V1 and V2 irreducible? And for one, it is very obvious to see. One is a one-dimensional vector space over here. For the other, the answer is yes, but you'll have to work it out. So heuristically, what we know is that the number of irreducible representations is the same as the number of conjugacy classes. And this number is exact when we are talking about finite groups. Over there, we have got something like a duality. I mean, not a very exact duality, but the number of irreducible representations is exactly the same as the number of conjugacy classes. But when we go to some interesting cases like Lie groups, over there, this doesn't hold. So let me start with an example of a representation. So before that, define HK to be the space of homogeneous polynomials of degree k in this V1, V1, V2, Vn over complex numbers. So what I can say is that HK, this is the linear span of summation Vi power alpha I. So I should be more precise than this. So product over alpha. So Vi power alpha I such that, and let's put some C alpha over here such that summation alpha I is equals to K. Okay. So this is exactly this vector space, right? Now, what I'm saying is that in this vector space, we just look at the H1 component. So H1 by this definition, H1 would be what? Just summation. So it would be linear, right? So it would be summation Ci Vi because it has to be linear polynomials, right? So this is H1. Now it's very simple to see that this H1 has got a Cn structure with Vi's being the basis. So naturally we have an action of GLN over here. And one can always identify this H1 with V. I can say that this is isomorphic to my V with the Vi being my basis. And now what we do is we extend this action from this V to all these HKs. This is what we call as the symmetric kth power representation. So this sort of a thing is something which we do a lot in representation theory, which is taking either the symmetric power or the exterior power. So here what I've done is, one thing which I claim and which I have already shown is that HK is going to be a vector space which has an action of GLN in C. So a question to ponder about is that are these irreducible representations of GLN C? And if so, then I have given an infinite family of irreducible representations. But are these all? I mean, how do we parameterize irreducible representations of GLN? And that is the question that we want to ask and answer over here. So I'll give you the answer for this one that yes, HKs are irreducible representations of GLNC and they correspond to some things. And I want to talk about those some things. So I'll be using two technique. I mean, there would be some technical theorems here and there, which for most reasons and purposes can be forgotten. Just remember this word, highest weight. So for every highest weight of GLN, there exists an irreducible representation with that highest weight. Okay, fine. There's something called as a highest weight. And here's a fact that every irreducible representation of GLN has a primitive element, which can be thought of as nothing but just not eigenvalue, the eigenvector. I'm sorry, this is eigenvector. So eigenvector of the upper triangular matrices. So this is something which comes from Cartan's theorem. Now, this is one of the technical theorems from Lie theory, which is called as the highest weight theory or highest weight representation. So if we use any irreducible G module with a primitive element, so we already know that every representation of G has a primitive element, and this primitive element has some weight lambda. What this means, I'll come to that in a minute. I just want to get this idea over here that this V would be a unique element up to multiplication by a scalar, and its weight is called the highest weight of this representation. And two irreducible representations having highest weight lambda 1, lambda 2 would be isomorphic if and only if these two weights are the same. Okay, fine. So there's something like a weight which parameterizes every irreducible representation. So we are not considered about any general group. Let's be very particular. Our group of interest is just this GLNC, right? And in the case of GLNC, this highest weight is a tuple. It's an n tuple given by lambda 1 till lambda n. Okay, where all these lambdas are integers, and we have got lambda 1 greater than equals to lambda 2 like this is in an increasing order. So let's say that the corresponding irreducible representation, we call it V superscript lambda, and the character is chi lambda. So here, I mean, I'm again recalling the definition of what exactly is the character. So the character was nothing but just the trace of that group homomorphism, right? So, I mean, well, this is my joke over here. So like how character defines a person. Similarly, the characters of representation tell us almost everything about a representation. Okay, so we have recalled what exactly is a character. Now let's come to the while character formula. And here's where the determinant identities would come. Before that, let me show you the, I mean, I should say the whole form of the while character formula. So here there's something in which we are doing a sum over what we call as the while group defined as the normalizer of the torus, modular of the torus. And then there's some sum happening on the top. This is just a formal sum, similarly a formal sum on the bottom. You see in the top part, there's a lambda parameter. There's no lambda parameter over here. So the denominator remains invariant. So this is the while character formula. We are not concerned about the general formula. What we are concerned about is just the formula in the specific case of GLN. Okay. In the case of GLN, if chi lambda was my character for the highest weight lambda, then one gets a very nice ratio of two determinants. So we have got determinant of xi power lambda j plus n minus j by xi determinant of xi power n minus j. Now xi, so one can ask what is g and what is xi? So g is an element of GLN, and xi can be thought of as the eigenvalues. Okay. So if I just say that these are eigenvalues, then it can happen that, well, this can't be then defined at anything where there are two eigenvalues are the same, and that is true. So in that case, one has to be very precise in saying that G is a regular element. That is, all eigenvalues are distinct. And regular elements are a dense set. So for all reasons and purposes, this is enough. And for those who have already seen the van der Monde determinant, you'll see that this thing over here is nothing but the van der Monde determinant. Okay. And we have the very nice formula for the van der Monde determinant. So this part over here, this denominator, as I said, it's independent of the lambda parameter. So this denominator is what we call as the while denominator. This has got a very nice description in terms of positive roots as well. Okay, let's talk about branching rules. So before going to the whole thing in a very abstract manner, let me just informally define branching rules. So suppose I have got H as a subgroup of G, and now if I have a representation of G, what we can do is we can ask what happens when I restrict that representation to as a representation of H. Okay. So if initially I started with some representation, this would break down. So we normally write it like this. So let's just say if V is a representation of G, then this I can restrict it to H, and that would give me some representations. Let's say some Wi's with some multiplicities Mi's. Okay, and these are representations of H. So the idea of branching is that we want to figure out what exactly are these multiplicities, okay, for the corresponding irreducible representations. So we don't normally use the term branching for any sort of a restriction. Only when G and H are considered to be Lie groups, semi-simple or reductive, that's when we start calling these as branching groups. I mean, this is just, representation theory is being pedantic about the names. So this is sometimes called branching rule, sometimes called branching laws. In physics, so this firstly started by the work of Hermann Weyl. He wrote a book on quantum mechanics, and in that, he used the terminology symmetry breaking. So this sort of a symmetry breaking operator is something which is very important in quantum mechanics. It allows you to take a higher level symmetry to a lower level symmetry. So whenever you're working with something like Noether's theorem, where there's some symmetry and then there's some conservation law. So all of those places require a lot of this symmetry breaking coming in picture. All right. Now let me give you the formal definition of branching rules. So if G is a connected reductive algebraic group and H is a connected reductive subgroup of G. So for all reasons and purposes, you should always imagine GLN and GL1 cross GLN minus 1 over here. Now, as I said, one can have something like a dominant weight. So for GLN, we saw the dominant weights were indexed by lambda 1 greater than equals to lambda 2 like that, right? So we've got a highest weight for G, and we have got the irreducible representation. And then what we do is we look at the character for this, we restrict it to H, and then again, we'll be having these multiplicities coming in. So now the multiplicities over here, we know that the parameters for the irreducible representations are highest weights, right? So here this lambda is the highest weight for G, nu is the highest weight for H. So what we want to do as a branching problem is to understand these multiplicities as a function of lambda and mu. So one is a parameter which is indexing the irreducible representations of GLN. The other is a parameter which is indexing the irreducible representations of GL1 cross GLN minus 1. All right. So let me just give the statement over here, the exact precise statement of branching, which Hermann Weyl proved. So so like in GLN, we had indexing from 1 to n plus n. Here we'll be having in GLN plus 1 from 1 to n plus 1. So here the branching multiplicity. So if I start with some highest weight lambda, and let's say nu is a highest weight of GLN. So the so this multiplicity would be 1 if and only if nu interlaces lambda. Now this interlacing condition is something which says that if it interlaces, then it is 1. If it doesn't interlace, then it is 0. Now this is something which is very beautiful if you were to ask me, because somehow it's just coming out without you trying a lot. This is what we call as a multiplicity free theorem, which is to say that the multiplicity is either 1 or 0. Okay. So let me give you the structure of how we'll be proceeding after this. So till now, I mean, I had talked about some generalities, some general picture. Now we'll be giving a proof of this branching rules. Okay. So first, what we'll be proving are Peary formulas, what we call as relative Peary formulas, and we'll be using some elementary properties of determinants for proving this. Then we'll do a cofactor expansion, like how we do a Laplace or a cofactor expansion on determinants. We'll do something similar over here for the Weyl character formula. And we'll be doing some computation here and there, finally, to get the branching rules. Okay. So let's firstly use this data, prove this relative Peary formula, which we are calling as the determinant identities. Okay, so I have a new notation over here, which I'm calling S mu, and I'm defining it by determinant xi power mu j. Okay, where mu i's are all in a strictly increasing order. So if I look at this notation, then I mean the y character formula, so chi lambda was given by determinant of xi power lambda j plus n minus j. The whole thing divided by determinant of xi power n minus j. Now look at this definition of S mu. So here, lambda j plus n minus j, this is also always going to be strictly increasing. Similarly, n minus j is also going to be strictly increasing. So with that definition, one can always define our chi lambda as s lambda plus rho by s rho, where rho is given by n minus 1, n minus 2 till 0. Now this corresponds to what we call as the half sum of positive roots for GLN. Okay. So, okay, that thing went away. But I mean, if you remember the the denominator was given by determinant of xi power n minus j, and we know that this is nothing but the van der Monde determinant, right? So this is I less than j, xi minus xj, right? So if I am to look at the Weil denominator for GL n plus 1, so what I can do is I can say that if I'm looking at that, so that would be determinant of xi power n plus 1 minus j, right? So I can write it as product I less than j less than equals to n xi minus xj times product I equals to 1 to n xi minus xn plus 1, right? So here, this is nothing but the smaller Weil denominator. So if I look at this ratio over here, which would be a ratio of this divided by this part goes away. So the only thing left is this, which exactly corresponds with this one. Here we have made the substitution with t equals to xn plus 1, which allows us to see that this product is symmetric with regards to all the xi's, but not xn plus 1. So this is what we'll be calling in our terminology as the relative Weil denominator. So this is coming as relative to two groups over here. Okay. And taking a tensor or taking a product of this relative Weil denominator with any representation and seeing how it decomposes, that is what we call as the relative theory formula. So this is the proposition. Now, if I was to ask Professor Rajan, he would say that we should not be putting our name over here. But well, I consider this to be the only cute result that we have in this talk. So the exact result that we have is that if I start with some irreducible highest weight representation, chi lambda, chi nu over here, and multiply it with this delta. Delta was the relative Weil denominator. Then it decomposes exactly like this. So you see here, I'm having chi nu plus epsilon. Now epsilon can be an element from 0, 1 power n, which is to say that this is like a z mod 2z power n. So this is an n tuple of zeros or ones. Okay. And this minus t power n minus mod epsilon. So this mod epsilon over here is just number of times one is appearing, just your classical mod, which is there in Rn. And the sum, this character is 0 if this is not dominant. So I'll come to this in a moment. Also, this thing which I've written over here, this is nothing but the expansion of the relative Weil denominator. We'll see how this comes in a moment. But first, let's prove the relative theory formula. So what we do is we just expand the definition of this relative Weil denominator. And we'll be just considering this numerator over here. Okay. So the numerator is this determinant. Now we make use of one property of determinant, that it is in n linear form. Okay. And now I've got n, a product of n different elements over here. So what I'll do is I'll take this xk minus t and I'll multiply it in the kth column. And that would give me something like this determinant, right? So this is something that we have been doing in since high school. So whenever we've got some n terms before a determinant, multiply it in the determinant. Now we'll be a bit clever with expanding this. So what we'll do is we'll be expanding this along the rows, but we'll expand it in a manner so that whatever is left behind, they would be something which are like the numerators in the Weil character formula. So let's just look at a very simple small case. So if I had, let's just say just x1 and x2. So I had x1 plus mu1 plus 1, x1 minus t, x2 mu1 plus 1, x2 minus t, and then x1 power mu2, x1 minus t, x2 power mu2, x1 minus t. Now, if I just look at this top part, one can see that we will be getting two terms over here. So we'll be having x1 power mu1 plus 2 minus t, x1 power mu1 plus 1. And similarly, the other one would be x2 power mu1 plus 2 minus t. Excuse me, I'm sorry. X2 power mu1 plus 1, right? So what we can do is we can just look at these terms which are not having the t's in one row. and look at the terms which are having the t in the row, and we can expand along that. That is to say that we'll just separate out the terms which are having the t, and we'll just expand the determinant like that. We'll be getting 2 power n distinct terms coming with this. Okay. And that would give me an expansion like this. Now see this minus t power n minus mod epsilon, this comes out common from there. Now for a moment, let's just look at what exactly this means over here. Okay. This would tell us what's going to happen next, why only the dominant ones are wrong. So for this to be dominant sort of a thing, we'll have to have that this nu plus epsilon I, these have to be in an increasing order, right? So let's just say they're not in an increasing order. So let's just say I have that nu I plus epsilon I. This is strictly less than nu I plus 1 plus epsilon I plus 1. So epsilon I is the ith component of epsilon that we had chosen over here, right? So I know that I started with something dominant bit. So we had that nu I is greater than equals to nu I plus 1. And this epsilon I can have at most value 0 or 1. I mean, the only possible values are 0 or 1. So this forces nu I to be equals to nu I plus 1. And epsilon I has to be 0 and epsilon I plus 1 has to be 1. Only then can it happen that this is not dominant. And if that happens, then you can see that in this determinant, there would be 2 rows, which would be the ith and the I plus 1th rows, which would be having the same exponent coming for the xjth term. And that would say that I've gotten 2 identical rows, hence the determinant would be 0. So this goes on to say that this sort of a sum, this survives only when this is dominant. And if it is not dominant, then this vanishes. Now what we just have to do is we just have to divide this whole thing by S row, and that gives us the formula that we initially started with, right? Divided by S row, we exactly get this. All right. So now we have gotten the tools. So the only thing left behind to do is to look at what we call as cofactor expansion. The same notation now, it's just that, we'll be working with n plus 1 tuples, and I'm abusing notation over here by calling the same thing S mu, but I hope it would be clear by context what exactly is S mu. So we'll be doing a cofactor expansion. Now let me explain what I'm doing over here. So let's work with a 3 cross 3 case so that it's easier to see what's happening. So I've got x1. Let's say there's mu1 plus 2, mu2 plus 1, mu3, x2, mu1 plus 2, x2, mu2 plus 1, x2, mu3, x3, mu1 plus 2, 3. So we have got the determinant of this, right? What we'll do is we'll expand along this column. Okay. That's what we call as cofactor expansion or the Laplace expansion. So expanding along the columns, what that would give me. So firstly, this would be like plus minus plus, right? So I'll be having x3 power mu1 plus 2. And then there would be this matrix remaining, right? So along with that, we'll be having determinant of x1 power mu2 plus 1, x2 power the same thing, and x1 power mu3. Again, x2 power the same thing. Then there would be a minus x3 power mu2 plus 1 determinant. So see, we are looking at this x3, so this and this term is there, right? So we'll be having x1 power mu1 plus 2, same power with x2, and x1 power mu3, and same power with x2. And lastly, we'll be having plus x3 power mu3 determinant of x1 power mu1 plus 2 x2 x1 power mu2 plus 1 and the same powers with x2, right? So what I want to do is I want to express this in terms of, so I want to express this part in terms of something like s of a some let's say lambda plus rho prime, where this is for a smaller one. If I do that, then I'll see that this specific one, this corresponds with nothing but mu2, mu3 as the highest weight. This corresponds with mu1 plus 1, mu3, and this corresponds with mu1 plus 1, mu2 plus 1. Right? I mean, this is just a simple observation that can be made over here based on how we have done the expansion. And if we do that in the case of GLN, we exactly get this as the cofactor expansion. And here these mu i's are given by this formula. So you see what's happening is when we are doing the cofactor expansion, so like let's just say we did the cofactor expansion for the first row. So then this part, this mu1 is omitted. So everything behind mu1, that would be coming invariant. Here we are doing the cofactor expansion along the second row. So whatever is coming before the second row, that would be having a plus 1, like here in this case. And whatever is coming after this would not be having any plus 1, like here. Similarly, you see here in case of mu3, whatever is, so there's nothing below this. So whatever is occurring before that, that would be having a plus 1. So if you look at this formula, you look at this formula over here. So this mu1 plus 1, mu2 plus 1 till mu I minus 1 plus 1, and the mu I term is omitted. And then mu I plus 1 and everything, they're remaining just like that. So what we can do is we can do this cofactor expansion on both the numerator and the denominator in this wild character formula. And we'll be getting something like this. Now, again, we use the same idea that, we'll just put xn plus 1 to equals to t. So here, this rho prime would be, again, sum of half roots corresponding to GLN. And these omega n's are what we call as fundamental representations, sometimes also the exterior power representations. And these correspond to weights k times 1 and then zeros. Okay. So after we divide this after we divide this numerator and denominator by s rho prime, that would give us exactly a wild character type formula for GLN, right? So once we do that, then we get this formula over here, which we call as the relative wild character formula. Now see, what we have done over here is that this was to look at this one. This was the whole wild denominator, right? And we divided this wild denominator by the wild denominator of the smaller one, which exactly gives us the relative wild denominator. And this exactly was the formula for the relative wild denominator, which we saw in the statement for the PRE. Okay. So one thing which I would like to mention over here is that this lambda n plus 1, it can always be made into 0. So this t power, which is coming as the lowest t power, we can always try to change it in a manner that this becomes 0, because one can tensor with sufficient power of determinant for that. So determinant is something which has, so determinant is also a representation, right? It's a one-dimensional representation. And corresponding to determinant, the highest weight is just 1, 1, 1, 1, 1. So if I had some representation, let's say some v lambda, and I tensor it with this determinant, then what would happen is it would give me v lambda plus 1, 1, 1, 1, 1. So similarly, I can do a determinant inverse, which would subtract a 1, 1, 1, 1, 1. So in essence, what it allows us to do is it allows us to make so that one of the things can be made into a 0. And we are choosing last quantity to be 0. Okay, let's start with a proof. And I would like to mention over here that what our proof is what we like to call as a long division. So the way we are doing this proof is that we'll be dividing this quantity by this quantity. Our method is somewhat ulta, somewhat going in the reverse manner, because what we are doing is we are going to look at what's happening for the constant term instead of the highest degree term, because the highest degree term over here would be having some unit attached with it. One can work in the opposite manner as well. Both of them are possible. We just are doing in this way because for the other cases that we consider, which is, the odd to even orthogonal or the symplectic, over there, consider starting from the constant term is a much easier approach than starting from the highest degree term. Okay. So the way we do this is that we'll just do a cross multiplication first. We'll take this relative wild denominator and we'll multiply it over here with this chi lambda. And we'll do a comparison of things. So here again, we invoke one thing from representation theory of groups, that any two characters which are irreducible are linearly independent. So as I said, we can always assume that this lambda n plus 1 is 0. And because the whole thing was a homogeneous thing in terms of all the variables, so this t parameter, which was the xn plus 1 parameter, it would try to maintain the homogeneity in some certain manner. So what we'll be doing is we'll be doing an induction on t, on the degree of t. And what we do is we do a comparison of the lowest order terms, which is the constant terms. So we anyway said that the constant term is from this, one can see that here the constant, so as lambda n plus 1 is 0, so the constant term is nothing but chi lambda n plus 1. So this superscript bracketed n plus 1, we already defined what it means, right? So we do that and we just make use of this linear independence of irreducible characters, and that exactly tells us that there is exactly one representation for which this would happen, and that representation would be this lambda n plus 1 minus 1 1 1 1 1. So this 1 1 1 1 1 again is coming from this part over here. So this chi omega n over here corresponds with the determinantal character. Sorry. Yeah. And the multiplicity on one of the sides is exactly 1, which tells us that this multiplicity of this nu, which is lambda n plus lambda n plus 1 minus 1 1 1, that is exactly going to be 1. All right. So our base case of induction hypothesis is done. So now let's proceed with the induction hypothesis, where we assume that the induction hypothesis is true for all r less than k. So we'll only be supposed to prove the induction hypothesis for k, and that would complete our proof. So in our induction hypothesis, we are assuming that the theorem which we had defined, that interlacing thing is going to hold for anything which is corresponding to degree less than k. So here this symbol is for saying that nu interlaces lambda. Okay. I'm sorry, that should have been nu prime, not nu. That should have been nu prime interlaces lambda. So the way we work with this is that we would just multiply the whole thing by the relative wild denominator. Okay. Now we exactly understand what these are. We don't really know what this m nu over here is. So here I have substituted the lambda notation. So it should be m lambda nu, but since we have fixed a lambda and then working, so I have substituted the lambda notation. So we can use the relative theory over here to see exactly which things are going to occur in this one after taking the tensor with delta. So if I go back a few slides and show you exactly the relative theory. So just look at this formula. We have this, and then this expands into something which is getting summed over these epsilons in 0 1 power n. There's a minus t parameter in this, right? So we just take this product, we multiply on the inside by that. And now what we want to do is we want to look at the t power k term contribution. So if we do that, then the t power k term contribution comes exactly from this term. Now this is computation which can be done. So this part which you're seeing in the bigger bracket, that is coming explicitly from the Peary formula. And what we're doing is we are collating all the t power k terms coming in all the different degrees over here. And that's exactly what this formula tells us. So what we're supposed to do, so you see, after multiplying by delta, the term that we'll have to consider here in this part, it would not be chi nu. So multiplying by delta, the only contribution which would be coming over here would be from t power k. So anything which is having degree greater than k, that can't contribute, right? And for degree k, the contribution can come only when we are looking at the product with the constant term. And I'd shown that the constant term was just the determinant. And the determinant would just increase the power. Would just increase it by this omega n. So omega n over here corresponds to 1, 1, 1, 1, 1 n times. Okay. So this is the term that we'll be getting. And what we want to do is we want to understand the multiplicity of this term. Okay. So here the multiplicity of this was given by m nu, right? And what we'll do is we'll say that the multiplicity of this nu plus omega n in this previous one, in this one over here, that we are calling as p nu. Okay. So we will compute the multiplicity of this multiplicity p nu by some combinatorics. And you see what's happening is that m nu plus p nu, this would be equals to the multiplicity in the numerator, in the Weil character formula numerator, right? So this would be the final thing that we'll be using for figuring out what exactly are the branching rules. So we changed the indexing a bit. So initially we were counting with regards to epsilon. Now what we do is we count with regard to this epsilon prime. Sorry. Now we can't count with this epsilon prime, where nu prime would be given by nu plus epsilon prime, and epsilon prime is given by omega n minus 1. So this corresponds to just saying that we are having 1, 1, 1, like that 1 minus epsilon. This makes perfect sense because, this can be either 0 or 1 in any of the entries. Hence, this would also be either 0 or 1 in any of the entries. And because this was running over the whole of, 0, 1 power n, this would also be running over the whole of 0, 1 power n. All right. With this, we firstly claim that if nu is a weight which for which the multiplicity is non-zero, then it has to interlace. So let's first come to this lemma. Sorry. That if nu is such that this weight, nu prime, which is nu plus epsilon prime, this interlaces lambda for some epsilon prime in 0, 1 power n, then this necessarily holds true. Okay. This is actually a very, very simple statement. So what this is saying is that I have that lambda I is greater than equals to nu I is greater than equals to, is greater than equals to nu I plus epsilon I is greater than equals to lambda I plus 1, right? So the possible values for epsilon I are 0 or 1. So if this is 0, well, nothing changes. But if this is 1, then certainly, this inequality holds. Then also, nu I would be less than lambda I, but then nu I would be greater than lambda I lambda I plus 1 minus 1. So when this epsilon I is 1, then this part of the inequality holds. Okay. Now, if we come back a bit and look at this formula over here, so we see that everything over here is of the form nu prime plus epsilon, right? So this would be so anything which is going to give a contribution would be something like this. And these have to be those which are getting interlaced. So anything which is not weakly interlacing, certainly the multiplicity is 0, because over there, this part that we wrote, this p nu would be 0. And those, one can then later see that they certainly would not be occurring in the Weil numerator. So this ME would also be 0. Okay. Now let's do a small counting over here. So let's just say M is the index. M is all those indices I such that nu I. I mean, we are counting the extremas over here. Okay. So we want to see what extremas are occurring. So we have that nu I is lambda I plus 1 minus 1, which is to say that it is coming exactly in the lower bound. And M prime is all those for which it is exactly equals to the upper bound, which is lambda I. And M and M prime are their cardinalities of M and M prime. Okay. So if we have that nu is a weight which is satisfying this weak interlacing, and there exists some epsilon prime such that this actually interlaces. If that happens, then you see for this to interlace, what would happen is that we'll have to mask up all those places where this was becoming exactly lambda I plus 1 minus 1, right? So all those places where it is reaching this lower bound, we'll have to add a 1 so that it does interlace. So how many ones we'll have to add? We'll have to add all as many as there are in this M, which is exactly this M. So at least M many ones have to be there, which gives us a lower bound for this mod epsilon prime. And for all those where it is exactly equals to lambda I, it has to be 0. I mean, epsilon prime has to be, epsilon prime I has to be 0, which says that it has to be less than n minus m prime. Okay. So one can ask, fine. So we have got this m prime, we have got this n minus m prime. And then epsilon can vary in between. So the thing is that this in between thing, we'll have a freedom to choose anything and everything over there. All of those would be free choices. They would all be occurring in some of the other previous part of the induction. And because these are free choices, so it is to say that I have got, let's say, n minus m prime many places. Okay, to be filled with mod epsilon minus m many things. In how many ways can I do that? It's exactly this choice. This is the binomial choice over here, right? So this is just a simple counting argument as to how many, I mean, what is the freedom that we have and how many we can freely fill over there. And this is the final answer. Now what we do is we put that multiplicity over here. So this was the initial formula that we had started with, right? So you see, this is the initial formula that we started with. So we were looking at the multiplicity exactly corresponding to this one. We saw that it is something like n minus m prime. Choose mod epsilon prime minus m prime, right? Which was this multiplicity. Now what we do is we plug in that multiplicity back over here and do the sum. So now this is nothing but just a binomial sum. So this is a famous binomial identity, right? Summation minus 1 power I. So I goes from 0 to n and choose I. This is 0. So if I was to do I goes from 0 to, instead of 0, I do a 1 to n of minus 1 power I and choose I. This would be minus 1, right? So in this case, we are having three possibilities. So you see, the small m was counting how many nu i's were there, which were exactly equals to lambda I plus 1 minus 1. So m being 0 means that nu I is getting perfectly interlaced. Okay. And if m is 0, then you can see that here we can do the counting in a here the counting would then be done from mod epsilon prime, and mod epsilon prime was strictly greater than 1, right? Hence, we will be getting a minus 1 over here. If m plus m prime, this is equals to n. So if m plus m prime equals to n, then that says that this mod epsilon prime can take exactly one value. Because we have that n minus m prime, this would be equals to m then, right? So this gets sandwiched to exactly m. which says that we have got exactly one term coming over here, which would be just a 1, which would correspond to exactly the mth power over here, n minus m prime coming over here, right? And that would give us this minus 1 power m. And it is going to be 0 otherwise. So the 0 otherwise would be coming because of this case. Okay. So once that happens, now these are the values that p nu takes. Okay. So the things which are occurring in the while numerator are exactly those. I mean, these things which are occurring over here. So this lambda n plus 1, lambda n plus 2, and like that lambda 1. These are all those for which this m plus m prime exactly equals to n, and m is greater than 0. And if we do that, then we'll see that this p nu and the thing coming here in the numerator, they exactly cancel each other, which tells us that m nu has to be 0. And in the other case, we'll be having that the thing coming here, I mean, the contribution from the right-hand side is exactly 0. So in the case when m is equals to 0, we are having that p nu is 1. So m nu has to be 1. Sorry, this p nu was minus 1. So m nu has to be 1 for this whole thing to be 0, which says that the multiplicity is exactly 1 when this interlaces and 0 otherwise. Now the proof in case of, so here I'm just stating the things for spin. So spin is what we call as a double cover for this orthogonals. So we have got SON, and we know that pi 1 of SON, this is Z mod 2Z, right? So this is not a simply connected group. What we do know is that the universal cover of any Lie group is also going to be the Lie group. So the universal cover for this is what we call a spin in. Okay. So constructions for these are also things that people have been looking at since ages. Now what happens is that for the spin, a small thing changes, that the highest weights, they would again be indexed by 1 to n. And here these lambda is, they're either all integers or all half integers. Okay. And here the branching rule is again going to be exactly like how we had in case of GLL. And the proof is almost exactly the same as well. It is just that the numerator changes a bit, and the things that we multiply, I mean, the relative theory almost stays the same. It's just that the numerator changes a bit. So one has to be a bit more particular regarding how exactly things are coming. And that is why we are having this mod nu n coming in the end to account for some extra things. Okay, so that finishes my talk. Here are my references. The one book which I referred to the most in this would be Goodman Wallach, and the next would be Fulton Harris. So if anyone wants to enter into this area of representation theory and wants a good introduction, then this Fulton Harris book is very amazing. And this was the book of Herman Weil, which I had mentioned, where one first sees Lie groups and the representations. So this is Monaghan's book, in which the first proof for spin has been mentioned. And the relative theory formula, which I had mentioned, they were inspired by this work of Soichi Okada on theory rules for classical groups. And here, so this one, branching rules for classical Lie groups, is the preprint that me and Professor Rajan have submitted. So we have already submitted in Journal of Algebra with our fingers crossed. Let's see. And let me just give a thanks to the people who have been constantly here and helping me around. So Samir is currently in Ashoka. He's teaching over here. Niladri and Monodeep, these are visitors at Ashoka. They're also PhD students at TIFR. Mohit used to be my batchmate, who was also my office mate, and almost everything which I have done over here, I have discussed it at least twice with Mohit. This guy is Jitendra. This guy is Debindu. Jitendra was again my office mate, roommate, flatmate. I mean, we spent a lot of time together. We discussed a lot of maths together. Debindu is a student of Dipendra Prasad, and he was visiting over here. We also work in some pretty similar areas. So we have been discussing about these things for quite some time. And last but not the least, here's Professor Rajan, along with our whole company of people. Thank you.
Okay, thank you.
I like to end by quoting this quote by Einstein, as far as the laws of mathematics refer to reality, they are not certain. And as far as they are certain, they do not refer to reality. This is just to say that pure mathematics is also interesting, but nothing pertaining to reality.
Thank you. Thank you very much. Any questions? Any questions for the speaker or comments?
Did I go too fast or something?
No, no, you find perfect timing. So, by the way, let me. Okay, so then let us thank the speaker and then I will stop the. Please unmute your.